Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, students, to another exciting session where we're talking about Newton's laws of motion. Okay, so today we will be talking about the three laws of motion. There are three of them, three laws of motion. Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. Okay, we're going to be talking about these, we're going to be summarizing them, and inshallah, we will be talking about applications as well and where we see them and use them in our everyday lives. Okay, so as we are used to in this channel, what I'm going to do is I'm going to read through it, I'm going to answer the questions, and I highly urge you to please pause the video and answer the questions as we go along and try and check your answers with me by playing the video after you've paused it. Okay, let's have a look. My Planet Diary. So this is a snippet from Sir Isaac Newton's diary, and here he is talking about his third law of motion, or an example of his third law of motion, which we will come to be familiar with shortly. If a horse draws a stone tied to a rope, the horse, if I may say so, will be equally drawn back towards the stone. Interesting. Scientists have used everyday examples to explain their ideas for hundreds of years. The quotations from Newton's Mathematical Principles of Natural Philosophy, which was first published in the 1680s. Wow, that's 400 years ago. Newton used this book to set down his laws of motion. These three simple laws describe much of the motion around you, and they continue to be studied today. See, the good thing about physics is it doesn't really change. These are the laws of the universe. Physics and science, generally speaking, is the science of the universe. It's the science of the rules that govern our universe. Let's answer this question here. What current scientific discoveries might be taught in schools hundreds of years from now? So, what current scientific discoveries have we as humans discovered this year, or perhaps this century? The most obvious one to me is electricity. I think that's a really obvious one. Just gonna write that in, electricity. I mean, compared to what they had 400 years ago, um, there are tons of examples. Scientific discoveries. We can talk about string theory. We can talk about nuclear physics, which is the nature of the atom. That's a relatively new thing, especially if we're talking about um, the energy levels. Okay, what is Newton's first law of motion? What's the first law of motion? You will be surprised if a rock started rolling on its own or a raindrop paused in midair. If an object is not moving, it will not start moving until a force acts on it. If an object is moving, it will continue to move at constant velocity until a force acts to change its speed or direction, basically changing its velocity. So Newton's first law of motion states that an object at rest will remain at rest unless acted upon by a non-zero net force, and an object moving at constant velocity will continue moving at that constant velocity unless acted upon by a non-zero net force. So let me just summarize what this says, because this just all sounds lovely, but let's try and make sense of it. So what that's saying is this: if I leave the room and I come back in right now and I see that somebody's moved my phone, okay, if somebody's moved my phone, which I'm leaving on this table here, then obviously, um, it didn't move on its own, right? So the first thought in my head, if my phone is no longer in the place that I have left it, I would say, who has moved my phone, right? Now, some of you might be thinking, well, it could have been the wind, it could have been um, someone else, it could have been, well, that's exactly the point, is that it couldn't move on its own. Something must have moved it because it will stay stationary. Okay? And likewise, if an object is moving, especially in a situation where there's no air resistance, where there's no gravity. Let's say in outer space, if an object is moving at constant velocity, it will not stop. It will never ever stop. Why not? There's nothing to stop it. There's nothing to stop it. There's no friction to slow it down. There's no external force to deflect it or change its direction or change its speed or anything like that, so it would continue moving. It sounds very obvious, but it's just one of those things you have to really think about. Yeah, so here on Earth, for example, if you roll a ball, it's quite normal that, of course, the ball will stop after a while. But why is that? Because there's an external force slowing it down, namely friction, whether it's friction with the ground, which is what we call sliding friction, rolling friction, um, stationary, static friction, and of course fluid friction. So there's air resistance to slow it down. Those are external forces. Those are external forces which slow it down, okay, and eventually make it stop. But if that ball was in outer space, it would not stop. So an object that's moving will never stop unless acted upon by external forces. And an object that is not moving will not start moving unless acted upon by an external force. Simple enough, isn't it? So that's the first law. I'm going to summarize it over here. And this is the way I'm going to say it. I'm going to say it in my own way, and I'm going to say it this way. An object does not want to change what it's doing. That's it. It doesn't want to change what it's doing. If it's stopping, it doesn't want to move. If it's moving, it doesn't want to stop. That's it. That's basically the first law of motion, right? It's also known as the law of inertia, the law of inertia, but we'll come to that on the next slide. What is inertia? So remember how we just talked about how some objects are not moving while others are moving? Well, here's the deal. I want you to think about two different objects. So, I love sketching, so I'm just going to do that. So I've got a big giant boulder over here, and here's a person for scale. And I've got a smaller boulder down here. Now, which one is going to be easier to move? The big giant rock over here, rock A, or is it the smaller rock over here, rock B? I think most of you know the answer to that one. Obviously, rock A is going to be a lot harder to move, right? Because this one weighs about 50 tons, 50,000 kilograms, while this one weighs about 50 kilograms. So, what is the factor here? What makes things easier to move? Obviously, one factor is going to be the mass. So, turns out that is inertia. So, inertia is, thank you so much for this one student that gave me this analogy. Inertia is stubbornness. Okay? So, basically, when something is stubborn, it doesn't want to change. It is the property of not wanting to change. It's how stubborn you are. Okay? It's also known as laziness, like it's the law of laziness. So that's one way of describing Newton's first law, the law of laziness or the law of stubbornness. So if an object has more mass, it has more inertia, simply put. If it has less mass, it has less inertia. So the other way I want you to think about that is if it has more mass, it is more stubborn. It doesn't want to change. If it has less mass, it is less stubborn and therefore wants to change. Okay? There we go. So let's keep going here. So that is what that's talking about. And if you have your books with you, then I would highlight the following. Okay, so all objects move, resist motion, resistance to change. Resistance to change in motion is called inertia. So that is stubbornness, right? Inertia explains how common events including why you move forward in your seat when the car suddenly stops? Absolutely. So let me just talk about that briefly. Basically, if you're driving or if you're riding in a car and the driver suddenly stops, what happens to you? You move forward. Why do you move forward? Because you don't want to stop. Remember what we said. You don't want to change what you're doing. So you, as an object in the car, you're not going to want to stop. So even though the driver has applied the brakes, you're going to continue moving forward. It's also the same reason why over here, you see that? This roller coaster. That's why you feel every single uh, bend and the G forces involved because as it's moving, it's changing directions. But what happens to you is you don't want to change directions. So let's say, for example, it's going in a straight stretch, like in a straight line, and then suddenly it moves right or it moves left and changes directions. What happens to your body is you don't want to change. So you basically want to continue moving in a straight line, but it's moving in different direction now. So suddenly you kind of get jolted to the left and to the right and so on, which is part of the fun, obviously. Right, so let's continue moving. Inertia depends on mass. We've already explained that one. Some objects have more inertia than others, and that is to say, some objects have more mass than others. Suppose you need to move an empty backpack compared to a full one. Obviously, it's going to be a lot harder to move the full backpack. Right. The other thing worth noting here is I'm going to talk about asteroids for a little while. So, for example, here on Earth, obviously we get asteroids and meteors that hit the Earth constantly. Most of these burn out in the upper atmosphere because that is our layer of protection. We've got the oxygen, we've got the different gases, the nitrogen and such, and therefore our atmosphere is very, very good at burning up anything that comes from outer space. However, some of those bigger ones do come through. And when they do come through, they can cause quite a bit of damage. Now, that asteroid is moving with a lot of inertia. That means it's got a lot of mass and it doesn't want to change its direction, which is why they can be quite dangerous, right? And how would you counter that? Well, if it's big enough, if it's big enough and it's moving fast enough, it means it has a lot of energy. How do I know that? Well, in physics, we've got this law, it's called the law of momentum, which is momentum is equal to mass times velocity. We also have this other law called the law of kinetic energy, which is half mv squared. And both of these laws, as you may have noticed, rely on mass and velocity. So if you have a lot of mass and you have a lot of velocity, you have a lot of kinetic energy and you have a lot of momentum, and it's very hard to stop you. This is why it's very, very important to understand these laws, because if we have a chance to save the planet, we need to counter this amount of energy and this amount of momentum. And how do we do that? We have to send an object, in this hypothetical scenario, we have to send a rocket out to counter this asteroid. Now, what is imperative is that this rocket has to be traveling at very, very high speeds. Why is that? Because, well, it's going to have a lot of energy to counter this asteroid. How much energy? At least equal, or big enough to deflect the asteroid. So yeah, that is why physics is very, very important. We need to actually solve some real life problems using physics, and we use Newton's laws of motion for such problems. Okay, moving on. Anyway, that was just a side thing. A roller coaster is hard to stop because it has a lot of inertia. Use Newton's laws to, excuse me, just a second. Yeah, so use Newton's laws of motion to explain why you feel tossed around whenever a roller coaster goes over a hill or through a loop. Okay, because we already explained it, you don't want to change what you're doing. Good. So this is just a very, very simple answer. Basically, just going back to that first law of motion, remember, an object that's not moving doesn't want to move, and an object that is moving does not want to stop. So naturally speaking, you don't want to change what you're doing. So if a roller coaster is moving in a straight line, you're moving in a straight line. But if it suddenly moves to the side, you don't want to move to the side. So that's why you feel tossed around. So it moves to the side, but you want to continue moving straight. And then suddenly you're moving to the side as well, but then it moves to the other way and you're tossed around again. So that's why that happens. Okay, assess your understanding. Oh, I get it. Now I know that Newton's first law of motion states that things want to continue doing what they're doing. They are stubborn, they are resisting change. If I'm moving, I don't want to stop. If I'm stopping, I don't want to move. That is basically the first law. Okay, let's move on. What is Newton's second law of motion? And this one is a bit more mathematical, and it talks about the mathematical relationship between those three factors that we will come to cover. Which is harder to push, a full shopping cart or an empty one? Who can cause a greater acceleration in a shopping cart, a small child or a grown adult? Okay, so that is something that is a real life application. We've all been to the shop before, and obviously if you're pushing one of those shopping carts, most likely an adult is going to be able to accelerate their shopping cart a bit more. Why is that? Why is it that a grown adult is able to push that shopping cart with more force? Okay, let's explore that. Changes in force and mass. Suppose you increase the force on a cart without changing its mass. The acceleration of the cart will also increase. That makes sense. So here we have a shopping cart. Okay, and it's full of groceries. And obviously it is on these wheels. And as you're pushing it, of course, it's going to experience some sort of acceleration, which is change in velocity. Because remember, acceleration is change in velocity is Vf minus Vi over the time it takes. So it's going to accelerate, but in order to accelerate it, what did Newton say? What was that first law? An object is not going to want to change what it's doing unless there's an external force acting upon it. So something that is stopping doesn't want to move, and something that is moving doesn't want to stop, unless there's an external force. Okay, so this shopping cart doesn't want to move unless a force is applied to it. But once a force is applied to it, it's going to change its velocity, and it's going to move and be forced to accelerate. Right, so what is the relationship there? Well, it turns out the relationship is quite simple. This triangle here represents that relationship. Force equals mass times acceleration. Force equals mass times acceleration. Well, here we use net force, which is basically just like the overall remaining force, because usually you have well, you have one overall force acting on an object, but you have more than one force acting on it. So for example, let's say a book is sitting on the table, you usually have at least two forces acting upon it. You've got the force of weight due to gravity, and you've got normal force or reaction force from the table. Right? So what if an object, say for example, is moving at constant speed, let's say a car. If a car is moving at constant speed, you've got the weight of the car, you've got the normal force or the reaction force from the road, then you've got the thrust from the engine, and you've got the air resistance opposing the car's movement. You've also got rolling friction, but we won't worry about that. So you've got different forces, but overall you've got one overall net force. And we've talked about that in the previous video, so you can always go back to that if you're unsure. The previous video label is friction and forces, I think it is. Anyway, moving on. So the net force, when we can write force net. So what that means is net force is equal to mass times acceleration. What that's saying is that the overall force on an object is equal to the mass of the object and the acceleration of the object. So remember that example I was talking about with the Earth and the asteroid, yeah? Um, if I want to counter that asteroid that is coming to doom the Earth, I have to send an object that has a massive mass, or at least it has a lot of acceleration, right? And that is going to produce an overall big enough force to counter that asteroid. So basically, that is the relationship. As you increase the force, okay, if you keep the mass constant and you increase the force, you're going to have a massive acceleration. So if we go back to the example with the shopping cart, if I change the force by changing the person, then there's going to be more acceleration. And this is common sense, really. We all know that. So basically, if I'm pushing on the cart, I'm going to produce a lot of acceleration. But if my son pushes on the cart, he might not produce as much of an acceleration because he's a much smaller person, right? And likewise, if a much bigger person comes along and pushes on the cart, and the cart remains the same, as in the same mass, if it's the same mass, but then I increase the force, then what's going to happen to the acceleration? The acceleration is going to suddenly go up. Okay, so I'm just going to do some real examples here just to show you what that looks like. So let's say the shopping cart has a mass of about 20 kilograms, which is reasonable. And let's say I apply a force of 100 newtons, because force is measured in newtons, don't forget. So I've got force is equal to mass times acceleration. Okay, so if I apply a force of 100 newtons and the mass of the cart is 20 kilograms, then the acceleration is going to be 5 meters per second squared, right? Now, if somebody comes along and they push with a much higher force, let's say a much bigger person, John Cena comes along and he pushes with a force of 200 newtons, right? Now the cart still has the same mass, which is 20 kilograms. Suddenly the acceleration is going to be 10 meters per second squared. That's basically how it works, exactly like that. So that is the second law of motion, and I'm just going to label it here. Second law. The second law is that force equals mass times acceleration, or you can rearrange that so mass equals force over acceleration, or acceleration equals force over mass. Okay? Moving on, if I was just to highlight something on this page, I would highlight the following. Okay, let's have a look here. Newton realized the relationship found way in mathematical. That is the gist of it over here. Okay, so acceleration is equal to net force over the mass. Very good. Okay, so based on that relationship, which I'm going to rewrite over here, force, mass, acceleration, how could you increase the sled's acceleration? So here we have a scenario with a group of people on a sled being pulled by these huskies, and we would like to increase the acceleration. Well, we know that let me just try and fix that A. Acceleration is equal to force over mass. And so if I want to increase the acceleration, I have to either increase the force or I have to decrease the mass, don't I? So increasing the force means more dogs. That's one way of increasing the force. And if I want to decrease the mass, I can say less people, because they're obviously pulling people. So if I have less people on the sled, that's going to cause more acceleration. It's going to go faster. And if I have more dogs, it's going to increase the acceleration once again. it's going to go a lot faster. How could you decrease the sled's acceleration? How could you decrease it? How could you make it less? Well, that's the exact opposite of what we have here. If I wanted to decrease the acceleration, I'll have less dogs. And if I wanted to decrease the acceleration, I could have more people. Okay? And it's asking me to color this in, so I'm going to use my highlighter once again, and I'm going to try and use black. So here we had 4 dogs and 2 people. I'm going to have 6 dogs, and I'm going to have 1 person over here. So less people, more dogs. Whereas over here, I'd have less dogs. I don't like just having the 1 dog. That's not fair. At least 2, so they can play together. And more people. Okay, moving on. Acceleration is measured in meters per second per second. Yes, it is, because here's just a very quick snippet. Acceleration is equal to change in velocity over time, and the change in which is a equal change in v over t, and velocity is measured in meters per second, and time is measured in seconds. So you can see it is meters per second, or meters per second squared, or meters of second to the power of -2. All of these are correct. Okay. Anyway, that's just a side note there. Acceleration is measured in meters per second. Newton's second law shows that force is measured in kilograms times meters per second. That is unit is also called, sorry, this unit is also called Newton. Yep, so that's exactly the same. So basically, what this is saying is that Newton, which is the measure of a force, is equal to kg dot meters per second squared. So those two units are equal. Now, why is that? I'll just give you a brief breakdown as to why that is. So forces are measured in newtons, we already know that, but we also know that forces are equal to mass times acceleration. And mass is measured in kilograms, and acceleration is measured in meters per second squared. That's why. So that is the unit of force, and that is the unit for kilograms, and that is the unit for acceleration. And this is an equal sign to say that everything on this side is equal to everything on this side. That's what that means. So force is equal to mass times acceleration. And so newtons is equal to kilograms times meters per second squared. If you didn't know, the dot means multiplied by. So kilograms meters per second squared. That little pause, kilograms meters per second squared, or kilograms dot meters per second squared, means multiplied by meters per second squared. Okay, let's do some calculations. Every year in cities around the world, teams create cars, push them across platforms, and hope they will fly. Yeah, so this is a very famous event. They didn't want to mention the name of the sponsor. It is, in fact, Red Bull. I've been to one of these events in New Zealand. I didn't take part in it, but I've been to one and I've seen all sorts of silly creations. But every year they hold these events where members of the public are allowed to just make their own creations of these flying machines. And yeah, so they all tumble into the lake, but some of them travel a little bit further than others. So anyway. Unfortunately, the cars always end up accelerating down into the water. Of course they do. Calculate. What am I supposed to calculate? After that same car leaves the platform, what am I calculating? What am I missing here? I don't have numbers to calculate, or do I? Excuse me just a second, just to check if I have the wrong version of something. Yeah, I'm missing the calculations. I'm missing the numbers. I don't know why I'm missing the numbers. So in your books, you should have some numbers here. I don't have any. Okay, so I've got your book over here, so at least I've got another copy, so that's okay. On your book, it should say if 100 Newton force, if 100 Newton net force acts on a 50 kilogram car, what will be the acceleration? Right. So we've got 100 Newton net force, so F equals 100 newtons. And we've got the mass, which is 50 kilograms. M equals 50 kgs. That's easy enough. And we are being asked to calculate the acceleration. So we know that force equals mass times acceleration. We've got the force, we've got the mass, we need the acceleration. So acceleration is going to be force over mass, F over A, which is equal to 100 over 50, which is going to equal 2 meters per second squared. Don't forget the squared, please. That's going to be the acceleration. Okay, after that, same car leaves the platform. Gravity causes it to accelerate downwards at a rate of 9.8 meters per second square. What is the gravitational force on the car? What is the gravitational force on the car? Well, we know that force is equal to mass times acceleration, so it's going to be force is equal to, we've got the acceleration this time, and we've got the mass from before. Here's the mass. Mass is equal to 50 kgs. So it's going to be mass times acceleration, which is equal to 50 multiplied by 9.8 meters per second squared, and that is equal to 490 newtons. That is the answer. Okay, let's assess our understanding. What equation allows you to calculate the force acting in an object? So hopefully by now all of you know what the equation is going to be. The force acting in an object, or the net force acting in an object, is going to be the mass multiplied by the acceleration. Calculate what is the net force on a 2 kilogram skateboard accelerating at a rate of 2 meters per second squared. 2 kilograms, that is the mass. Acceleration is 2, so that's going to be force is equal to 2 times 2. I can't write it here because as I do that, these prompts come up. So I'm going to write the answer over here, 2 times 2, which equals 4 newtons. Okay? And next, predict if the mass of a skateboard is doubled, but the net force on it remains constant, what would happen to the acceleration of the skateboard? Very good question. It's going to half, but then let's find out why. Okay, so if the mass of a skateboard is doubled, let's just come up with that scenario. Let's say the mass of a skateboard is 10 kilograms, okay, which is a bit on the heavy side. So the mass is equal to 10 kilograms. That's just a number that I came up with. I came up with that number. But the net force on it remains the same. And let's say the force is about 50 newtons. Then what's going to be the acceleration? Acceleration is going to be 50 divided by 10, which is equal to 5 meters per second squared. Now what happens if I double the mass? If the mass of the skateboard is doubled, so let's say the mass suddenly is 20 kilograms, but the force remains exactly the same, 50 newtons, then suddenly the acceleration is going to be 50 divided by 20, which is 2.5 meters per second squared. So it will have, okay, right, moving on. Action reaction forces. This is finally the third law. So quick recap. First law. First law is things don't want to change what they're doing. If an object is moving, it doesn't want to stop. If an object is stopping, it doesn't want to move unless an external force is acting on it. Remember that last part, unless an external force is acting on it. Right, the second law is force is equal to mass times acceleration. The force acting on an object is equal to the mass of the object and the acceleration of the object, or the acceleration of the object is equal to the force acting on it divided by the mass, or the mass of the object is equal to the force divided by the acceleration. Right. And now the third law is for every action, there is an equal and opposite reaction. Two key words there, equal and opposite reaction. So here are examples of what we mean by that. A swimmer moves because the water pushes her forward when she pushes back on the water. So I'm actually sitting on one of those chairs that are like a swivel chair. Okay, so I'm going to move the table. I'm going to put some force on the table. So here I am. I'm pushing on the table, all right? I want you to see what happens. If I'm pushing on the table, what happens to me? I'm moving back, and I'm going to push on the wall now, and I'm moving back. So what happened? I pushed the wall, and then suddenly I'm moving forward. Why is that? Why is that? Because as I pushed the wall pushed back on me. Okay, so that's what we mean, is that for every action there is an equal and opposite reaction. When I was pushing on the table pushed back on me. So I pushed the table, but then suddenly I got pushed back. So that means the table pushed back on me. Okay, what if the table didn't push back on me? I would break the table, wouldn't I? But the table did push back on me, so that's why I moved back. Okay, what about if I'm just standing? Okay, like now I'm sitting on the chair. I'm sitting on the chair, there is a weight force acting downwards, right? So let me just draw that scenario for a second. I'm sitting on the chair, and it's not one of those chairs. Let me just draw the chair properly. It's one of those chairs. So I'm sitting on the chair, and there is a weight force acting downwards. But there's also a reaction force, what we call a normal force acting upwards. If there was no normal force acting upwards, then the chair would break. The weight force acting downwards would be high enough to break the chair, but there is a normal force acting upwards to counter the weight force acting downwards. And because these two things are balanced, I am lucky enough not to break the chair. Okay, so there is a reaction force the same way if you push on a wall, the same way if I'm disembarking this boat, if I'm about to move away, then the boat will actually react and move backwards. That is a similar scenario to what I just described. The book is sitting on the table because there's a reaction force, there's an action and reaction force, there's the weight force acting downwards, and there's a Newton, a normal force acting upwards. Now, if there was no normal force acting upwards, or if the normal force could not be equal and opposite, what's going to happen to the table? It's going to break. The table has to apply a force equal to the weight force. And what does apply a force mean? It means withstand it, or be able to handle that force. So if there's a weight force acting downwards, then the table has to handle that weight force, and handling that weight force is what we call a normal force. So basically, it is applying a force in the opposite direction, and it's equal to the weight force, which is why the book isn't going through the table. But if we take a quick example, if we just say an elephant is sitting on that table instead of a book, right? Then that table has to apply a force upwards equal to the weight of the elephant. That table, if it's not able to do that, what's going to happen to the table? It's going to break. It's going to break, which is what happens. Okay, we're going to explore the third law in a bit more detail in a minute. Here we go. What is Newton's third law? If you leaned against the wall and it didn't push you back, you'd fall through. You'd fall through. So if you lean against the wall, that's what I say, if you lean against the wall and it doesn't apply enough force, what's going to happen to that wall? It's going to fall through. If it doesn't push you back, what that means, that statement is just saying if it cannot handle the force you're applying on it, then it will fall through. The force exerted by the wall is equal to the strength. It is equal to strength and opposite in direction to the force you exerted on the wall. That is a very important point. Now, let me just use orange. The force exerted by the wall is equal in strength and opposite in direction to the force you exerted on the wall. And the two key words here are equal in strength and opposite in direction. So it has to be equal and opposite. Newton's third law of motion states that if one object exerts a force on another object, then the second object exerts a force of equal strength in the opposite direction on the first object. Another way to state Newton's third law is that for every action there is an equal and opposite reaction. Yep. So basically, that is to say, for every force there's an equal and opposite force. Okay? The reason why you are standing or you are sitting down on that chair is because the chair is putting up a force to balance your weight force down. Otherwise, the chair would break. And the same way, if you are standing up, okay, your legs have to support your weight. So you're putting down this weight force through your legs, and your legs are putting up a normal force to support you. Otherwise, and that's why you get tired. Okay, if you're standing up and you're wondering, why am I getting tired? Why am I getting tired of carrying my own weight? It's because you're supporting your own weight. You're putting up a force equal to your weight force. So your weight force is acting down through your legs. Let's say, for example, you have a weight of about 500 newtons, which is 50 kilograms more or less. 250 newtons would be going through your right leg. 250 newtons would be going through your left leg. Your legs have to, in turn, support 250 newtons each. So your left leg will have to support 250 newtons. Your right leg will have to support 250 newtons. And therefore, you're getting tired. Why are you getting tired? Because you're carrying 250 newtons in each leg. Okay? How am I going to reduce the amount of force carried in each leg? Well, not many options there besides losing some weight. Yeah, so that's the way it works. For every action, there is an equal and opposite reaction. And we have what we call reaction pairs. Okay, so we'll come to explore those a little bit in just a minute. Pairs of action-reaction forces are all around you. When you walk, you push backwards on the ground with your feet. Think of this as an action force. It doesn't matter which force is called the action force and which force is called the reaction force. No, it doesn't really matter. The ground pushes forward on your feet with an equal and opposite force. This is the reaction force. You can only walk because the ground pushes you forward. In a similar way, the swimmer in figure 3 moves forward by exerting an action force on the water with her hands. The water pushes on her hand with an equal reaction force that propels her body forward. So what this is saying is exactly the same demonstration that I showed you in the beginning. So basically, if I point this at this cabinet over here, and I'm pushing, okay, what's going to happen to me? I'm pushing on the wall. Watch this. I'm pushing on the wall and I'm getting pushed back. So one more time, let me show you that demonstration. I'm pushing on the wall, I'm getting pushed back, okay? Why is that? Why am I pushing on the wall and getting pushed back? Because for every action, there's an equal and opposite reaction. So I'm pushing on the wall, but I'm getting pushed back. So that means whatever force I'm pushing with, the wall is pushing back with the equal force. So let's be gentle to begin with. I'm going to be gentle. I'm going to push in a gentle manner. So if I'm pushing gently, I'm getting pushed away gently. What if I push in a harsh way? What if I push with a lot of strength? Okay, let's try that. I'm pushing with a lot of strength now. Wow, that really pushed me back. Okay. So basically speaking, the more force I apply, the more force is applied back on me. Okay. And if the cabinet cannot handle that, then it's going to break. Okay, I'm going to go right through and I'm going to break it. So that's basically it. It has to apply a force equal and opposite. Let me just show you that scenario very briefly. So what happened was, here's a cabinet, and here's me sitting on this swivel chair with wheels on it. Okay, so I am pushing against the cabinet, and I'm pushing with a force. And what the cabinet is doing is pushing back on me with a force that is equal and opposite. Okay, and that's it. That's basically it. That is an action-reaction pair. So this is an action force. I started by pushing, the force of push, and the reaction force There is a reaction force, and that is a pushback. And there's a reaction force of a pushback. Okay, so that's what we're talking about here. Let's answer this question. Action and reaction pairs are all around you, but they aren't always obvious. Write down a question about a situation in which you can't identify what force pairs outwork. They want us to write a question. I'm going to write this. What are the action, reaction pair forces, or what are the action, reaction forces when an object is falling down? So here's an object falling down. What are the action reaction pairs? What are the forces acting on the object that's falling down? There's the weight force, obviously, due to gravity. And what is the reaction force? The reaction force in the upward direction is going to be air resistance. Once these two are equal, what's going to happen? The object is no longer accelerating, so it's going to be traveling at constant speed. And that's what we call terminal velocity. So basically, when these two are equal in magnitude, then they are an equal and opposite reaction pair, action-reaction pair, and therefore the object is now in equilibrium. It is no longer accelerating. Okay, detecting motion. If you drop your pen, gravity pulls the pen downwards. According to Newton's third law, the pen pulls Earth upwards with an equal and opposite reaction force. Yes, that is quite crazy to think about, but don't worry, it will make sense soon enough. You see the pen fall, you don't see the Earth accelerate up towards the pen. So basically what this is saying is like if you have a magnet and you have a small tiny nail, and you bring the nail close to the magnet on the table. Let's say, for example, you bring the nail. Okay, I'm just going to draw this scenario. So you've got a nail. Here's a nail, not a very good one, but anyway, that's a nail. And oh, I can draw a better nail than that. Just as bad as the old one. Anyway, and here's a magnet. North, south. If I bring these two close to each other, then that is going to be attracted to that as much as this magnet is going to be attracted to this nail. So that's what it's saying. But now think about a different scenario here. Think about if the magnet was much bigger, if the magnet was a lot bigger, you might be tempted to say, well, the magnet is a lot bigger, so that means the nail is moving towards the magnet. Well, actually, the nail is moving towards the magnet and is attracted to the magnet as much as the magnet is attracted to the nail still. So how can we see the nail move towards the magnet, but we don't see the magnet moving towards the nail? Well, it has to do with the second law. Force equals mass times acceleration, right? So if there is a force acting on this nail, let's say the nail has a mass of 0.01 kilograms, while the magnet has a mass of 2 kilograms. And we have the same force acting on both, because of course the force is equal and opposite, right? Because of Newton's third law, we know that the force acting on each is going to be an equal and opposite. So we have a force and we have a reaction force that is equal and opposite. Right. So let's give it a number. Any number, it doesn't matter because they are equal and opposite. Let's say it's 5 newtons. So the force is equal to 5 newtons, the mass is equal to that. That's for the nail. That means the acceleration of the nail is going to be 5 divided by 0. 0.01. So that's going to be 500 meters per second squared. Now I'm going to apply the same scenario to the magnet. If the magnet has a 5 Newton force acting on it, but the mass of the magnet is 2 kilograms, then the acceleration of the magnet is going to be 2.5 meters per second squared. Clearly, you can see the difference in the acceleration. One of them is moving a lot faster towards the other. Okay, now I want you to imagine the scenario for the Earth. So the Earth is absolutely massive compared to this tiny little pen. And if the pen is accelerating, the Earth is not going to show hardly any acceleration towards the pen because of its sheer massive size. So it's all got to do with mass in this instance. The mass of the Earth is so massive. The Earth is acting like this magnet, but it's so massive that acceleration for the Earth is going to be in the order of 0.000000001 meters per second squared. You are not going to see this. You are not going to notice this. And that's what we're talking about here, is it's so tiny. It's such a tiny acceleration that you don't notice it. Okay. Let me just bring my highlighter out. Do action-reaction forces cancel? You have learned that two equal forces acting in opposite directions on an object cancel each other out and produce no change in motion. So why don't the action-reaction forces in Newton's third law of motion cancel out as well? Action-reaction forces do not cancel out because they act on different objects. The swimmer in figure 3 exerts a backward force on the water. The water exerts an equal but opposite forward reaction force on her hands. What you saw is a similar example. What it's talking about is a similar example to what I'm doing when I'm pushing against the cabinet. When I'm applying a force on the cabinet, the cabinet is applying a force on me. So I'm a different object to the cabinet. I'm applying a force on the cabinet. That is my action force. The cabinet is applying a reaction force on me. So that's why they don't cancel. Okay, so it's actually different. So because they are different objects, so why don't the action-reaction forces? We just explained that. Action-reaction forces do not cancel out because they act on different objects. Okay, the action-reaction forces act on different objects. The action force acts on the water. That's just the example there. Now, here is an example where the action-reaction forces are acting on the same object. So on the ball, we've got action-reaction forces acting on the same object. What's going to happen to the ball? It's going nowhere. It's going nowhere because the action-reaction forces acting on it are exactly the same. So let me just get rid of this highlighter. Oh, I can't get rid of highlighter? That's crazy. Okay, didn't know that. Oh, I gotta zoom out first. All right, let me try that. So if I zoom out, oh, I can take it out. Okay, cool. Let's just zoom in again. Very good. And I'm going to use my pen. Oh, I still want to zoom in. I still want to zoom in and use my pen. So you see what's happening here. Oops. Oh, I can't try it when I'm zoomed in. Well, I'm learning new things. Okay, let's get rid of the zoom. Here we go. So over here, there's an action and reaction force acting on the ball, but because they're acting on the same object, it's not going anywhere. Because it's acting on the same object, it's not going anywhere. They cancel each other out because it's on the same object. The same thing happens over here. So here we've got two dogs, and both of them are applying a force on this object, and the forces are going to cancel out. Now, somebody might be saying, well, where's the reaction force? Well, there is a reaction force in the opposite direction from the box itself. So the box is applying a reaction force to each dog, but because it's the same object, they're both applying a force on the same object, the net force is going to be 0, and they're going to cancel each other out, and the box is not going anywhere. There you go. Okay, so here is a scenario. Um, yeah, so in order for a bug to fly through the air, a force has to push the bug forward. Identify this force. And okay, so this is basically one of those things where we have to talk about Newton's three laws, and let's explore which ones are relevant and which ones are irrelevant. In order for the bug to fly through the air, a force has to push the bug forward. Identify this force. How does the bug produce it? Hint, think back to how a swimmer moves through the water. Okay, so in order for the bug to move forward, what needs to happen? Obviously, the bug has to push the air backwards, and then the air has to apply a force forwards on the bug. Um, and the actual reaction force is how the bug is moved forward. So here's the bug. Oh, let's go back. Here's the bug. And what happens is it applies it applies a force backwards on the air, and the air is applying a force forward on the bug. The same exact thing that happens when I push the cabinet. If I push the cabinet, then the cabinet pushes me forward. Okay, I push the cabinet backwards, it pushes me forward. Okay, and so the same thing happens with the bug. The bug is pushing the air backwards and it's pushing itself forward. Okay, so um, action, reaction, forces. Bug pushes air backwards, air pushes bug forwards. Action, reaction. The bug was at rest on a tree when it saw the car and decided to fly towards it. If the bug has a mass of 0.05 kilograms and accelerates at 2 meters per second, what's the net force on the bug? Now, this first one was Newton's third law. Okay, this is the third law. I'm just going to do this, and that's just to show you which law we're using. In this one here, it's the second law. Second law, why is that? Force is equal to mass times acceleration. We have the mass, we have the acceleration, and we're being asked to work out the net force. So the net force is going to equal to mass times acceleration, which is equal to 0.05 multiplied by 2, and that is equal to 0.1 newtons. That is the overall net force. Okay? Let's look at scenario B. The driver hates killing bugs. When she saw one coming towards the windshield, she braked suddenly and hoped it would get out of the way. Sadly, it didn't. When she hit the brakes, she felt that she was thrown forward. Use one of Newton's laws to explain why. Interesting. Well, I'm going to go with the first one. I'm going to go with the first law. And it's the law of inertia. Basically, what we're working with here is that obviously the object did not want to change um, its motion. So even though the car stopped, she kept moving forward. Um, so that's why. So objects don't want to change their motion. So when she stopped, the object kept moving forward. That is, her body kept moving forward. Okay, let's look at assessing our understanding. Um, a dog pulls on his leash. A dog pulls on his leash with a 10 Newton force to the left, but doesn't move. Identify the reaction force. Um, okay, that's quite easy. Um, if the dog is pulling on the leash with a 10 Newton force to the left, but doesn't move, that means the leash is pulling to the right with a 10 Newton force. And this kind of force is called tension force. Okay, so here's the dog. It's not the best dog, but anyway. So here's the dog. He's got his tongue sticking out, and he's pulling on a leash with a 10 Newton force. But of course, the leash is pulling back with a 10 Newton force, which is why it's not moving. Use all three Newton's laws, explain how objects react to forces. Oi, that's a bit of a mouthful. Um, hmm. Okay, so I think what it's asking for here is let's talk about an object. Let's talk about a ball. If a ball is moving, it doesn't want to change its movement. So using all three Newton's laws, explain how objects react to forces. Using Newton's first law, we can state that an object doesn't want to move unless it's being forced to move, or an object will continue moving and will not stop or change its direction unless it's being forced to change its direction or stop. So that's the first law. Um, the second law states that that force, the magnitude of the force or the size of that force, is equal to the mass and the acceleration, the mass multiplied by the acceleration. And the third law states that for every action there is an equal and opposite reaction. That is to say, when a force acts on an object, the object applies an equal and opposite force back. So yeah, so let's try and put that in words. Objects don't want to change motion unless an external force is applied. This external force, the force acting on an object, is equal to mass multiplied by the acceleration. So F equals ma. And the third one states that when a force is acting on an object, an equal and opposite force is reacting to it. So for every action, there's an equal and opposite reaction. This is the first law, this is the second law, and this is the third law. That's it. Okay, we've got another scenario to deal with here. The unfortunate bug hits the windshield with a force of 1 Newton. That's the force, the net force. If you call this the action force, what is the reaction force? Does the car hit the bug any harder than the bug hits the car? Use one of Newton's laws to explain why or why not. So the windshield hits the bug with a 1 Newton force. Right. So Does the car hit the bug any harder than the bug hits the car? No. The car hits the bug with a 1 Newton force. The bug hits the car with a 1 Newton force. So this is the third law. For every action, there's an equal and opposite reaction. Using the third law, we know both action and reaction forces are equal. Okay? Compare the forces on the bug and the car again. Use another one of Newton's laws to explain why the bug goes splat and the car keeps going without noticeably slowing down. So the same force acts on both, obviously, but this time I'm going to use the second law. Second law. Why is that? Well, even though the same force acting on both, we know that the force is exactly the same, the mass is different, and therefore the acceleration is going to be a lot different. Since the mass is different, the acceleration is going to be much, much more for the bug than it is for the car. And so forces are the same, but bug much smaller. Bug, this is horrible writing on this glass. Bug acceleration much bigger. Why is that? Because the force is the same, but the mass of the bug is much smaller. Therefore, the acceleration is going to be much bigger. Okay, now I get it. Now I know that Newton's third law states that for every action, there is an equal and opposite reaction. And that is it for today. Now, I apologize. I know it was a bit of a lengthy session. I needed to explain things in boring detail. My advice is that you go back through this if you are struggling with it. Watch a few videos. I might actually recommend a few videos in the video description below. It's a bit of a tricky topic, but you know what? If you are persistent, you will understand it. إن شاء الله. Take care. نشوفكم على خير. السلام عليكم.